Okay, well, I think we're about 9:30. We're all ready to record? Excellent. So welcome. This is our September 2nd lecture, our second week. So we have homework number 1 is due next Tuesday. This is a hopefully reasonably straightforward stuff, just to get everybody up and running on rotating frames, basic, simple programs. But again, on these programs, even if you've written them before, I encourage you to kind of maybe go through them again. Look at them to where we're going to be going to multiple spacecraft. In fact, the last homework problem in that set asks you specifically to write it, I think, where it works for 2. And 2 is good. If you want to do more, that's fine. If you want to make it a loop for up to n, but you want to kind of go through those. So what we'll be doing today is kind of wrapping up the stuff with the two-body problem. So the reviews attendance are going to finish. We might get into perturbations already, but otherwise that will start on Thursday. That will definitely be new material, Lagrangian brackets and variational math that we'll be getting in. So it's a good tool that you have if you're going to do formation flying. So are there any questions on the first homework assignment right now? Any particular question? There was a question coming up on the 111, I believe, whether second or third edition has the same problem assigned for that?
First and third, but
yeah. The first and third edition?
Yeah, I don't have the second.
Ah, the first, I have no idea.
Okay.
It's about the free-body problem.
You have to have at least the second edition, yes,
Okay.
or the third. Okay, that's why then there was a distinction. No, I don't.
What's the one?
The first one's been out of print for a long time. Sorry.
It's the one from 2003, whatever one that is. Is that the first?
Yes.
Okay, yeah.
That would be the first edition. There was 2 printings of the first edition that had slight differences in it. But no, we've been on the second edition now for a good 7 years, and we're just now, this summer, moved over to the third edition. But people here who've taken 5010 would have had the second edition already. But if you have the first, there would be differences there. Yeah, I'm not sure what to say. I would say you should have at least the second.
I have the third now. So.
You have the third? Oh, then you're definitely set. Okay. Anybody else not have the second or the third edition?
I had the first edition, so I did the first 9.4, 9.5 were about the free-body problems.
Okay, yeah, no, definitely, it's the official textbook for the class is the third edition. If you still have the second, you're fine. The first is pretty darn old at this point. There's been a lot of little changes and fixes and examples, so those things won't match up. If you do that, get with a colleague who has another edition and you can fix it. I'm not forcing you.
The third one is just has to be delivered. So.
Oh, okay, cool. Then you're all set. Good. Anyway, so we all worked out then. Good. So homework on the 1 due in a week. Then there'll be 2 other homework assignments. So really, put effort into these things because it determines your grade. If you really bomb one of these, there's obviously not much opportunity to do it again. So any questions on the current stuff, on the coding? Questions on what to use? One of the homework problems, asks you to do these transformations from classical elements to Cartesian and a Cartesian back to classical elements. Those subroutines exist, actually. They come with the textbook. So, here, you're laughing. So is it good? Could you just use those and turn them in?
No, but you can use them to check your work.
Exactly. So again, if this ethics stuff quickly becomes fuzzy sometimes, I'm perfectly fine. They're there. You can find other ones. There's probably all kinds of things posted. You can, if you're really stuck and you go, man, I don't quite remember. Seeing somebody else's code might be really instructional to go, that's how you could do that. Great. But then you do have to write your own stuff and understand how that works, right? Because you need to own this code. Because afterwards, homework 2s and homework 3s in your project, you're going to be incrementally adding to this code. These subroutines will be embedded within other codes, and you need to own this stuff, not just try to use somebody else's code and crossing your fingers. It's just going to end up in a train wreck down the road, okay? So yeah, you're welcome to use those routines to check if you want to. If you find an error, let me know. I'll go fix mine. But do write your own stuff. Okay? No questions otherwise on the homework? Hopefully reasonably straightforward. And hopefully you started them already. So, back. Let's move on. So where we ended last time, we did all the stuff with Kepler's equation. So let's quickly review Kepler's equation. Patrick, what was Kepler's equation about? In simple words.
The area of an orbit tracing at equal.
That's one of Kepler's laws.
Oh, okay. Oh, well, I guess the equations were about
Kepler's
sections.
No, that's also one of Kepler's laws. Nick, what is Kepler's equation?
The thing that transforms between mean anomaly and eccentric anomaly?
That's the mean anomaly definition. It's not necessarily, that's not Kepler's equation. Sam? What's Kepler's equation? What is Kepler's equation?
It's the time of flight equation.
Time of flight. So just get to know, if I'm talking about Kepler's equation, and we'll be doing that a bunch, I'm just going, well, you know, now it's all done, we've got everything set up, all you have to do is solve Kepler's equation and we're done. I'm expecting you to know what I mean by Kepler's equation. So Kepler's equation is a time of flight problem. Where would the satellite be 6 hours from now? Where was it 2 hours ago? Right? And we showed last time if you use true anomaly, you end up with this really weird integral. This elliptic integral is hard to solve. If you map true anomaly into eccentric anomaly, the integral becomes much easier. And then we just defined that mean anomaly to be big E minus eccentricity times sine of big E, you know, the eccentric anomaly. That was the definition of it. Why did we go to mean anomaly, Sarah? What was nice about that?
That you could propagate it in time, like it consistently moves in time.
So it has a constant rate, right? And that even works for hyperbolas. That the things defined slightly different. It's not just the square root mu over a cubed, but it's square root mu over minus a cubed, because a for us hyperbola is negative and all that kind of things. But in the end, we've gone through this transformation, right? Anomaly means anomalous, weird kind of angle variations. The mean anomaly behaves like it were on a circle. And you know, hey, you know, so much time in forward, you've moved at 10 degrees per second on average, tells you where you are. Going one way is always easy. I'm telling you the angles, and you can solve, you know, hey, we're starting out at this angle, true anomaly, 30 degrees, and that later point we're at 60 degrees, true anomaly. You can go through the algebra, it's all explicit, and you will compute M1 and M2. With that, you can take a difference, divide by the mean rate, and you must have flown, you know, 0.67 hours, something. Wonderful. The reverse, though, can you do that, Carlos, explicitly?
No, you have to solve numerically.
Which method do we typically use numerically?
Newton-Raphson.
Newton-Raphson method. Yeah? So you need that partial quickly, you have initial guess, and just uses a steepest descent thing, and it will lock in on that very quickly. What do we use as initial guess for our, we're going for mean anomaly value, we want to find eccentric anomaly. Once we have eccentric anomaly, again, you have explicit formulas on how to go to true anomaly, so everything's good there. But what's our initial guess that works well, Steph?
I'm not sure.
Nicholas?
You mean the initial guess for E is usually our mean anomaly.
Exactly. If you just set your, okay, I have a mean anomaly of 36 degrees, or put that into radians, hopefully. It has to all be in radians. Then your initial guess is for reasonably small eccentricity, just make it equal to that. It's probably pretty close to that value. And then doesn't take many iterations with Newton-Raphson, and you'll be right on top of it. Where you start to have longer convergence issues is where it becomes close to E is equal to 1. Then things kind of get squirrely. And there's some textbooks like Batten. I don't know if anybody here knows of Richard Batten from MIT. Got this huge introduction to mathematics of astrodynamics. He has a whole chapter on nothing but ways to solve Kepler's problem in all kinds of weird situations. So it's a problem that comes up and up. So Kepler's problem means, Patrick?
So when it's time of flight.
Time of flight, yeah. And if you're going one way, great. But if I have angles, I'm trying to figure out where am I, what time I'm at an angle, I have to do this numerical iteration. So somewhere in your code, you should have something that does that quick iteration. And just make a subroutine that takes your M and gives it an eccentricity, and it does a few iterations and spits out that big E. Right? You want that code somewhere. Right? Very simple, just takes a few lines. Good. What else did we do last time? So we did the anomalies, the results, derivations of the stuff, and we also finished up the conservation laws, energies. So with the, if you're trying to solve for the orbit type, Lauren, what would you solve for? How do I know if it's a ellipse, hyperbola, parabola, circle?
You look at the energy.
Energy, okay. Do I solve for semi-major axes explicitly? That's something that will come up today. Why not, Lauren?
I'm trying to remember why. I know it's 1 over.
You solve for 1 over A.
If A approaches infinity, then that's tricky to deal with, right? So
And which orbit type makes A go to infinity?
hyperbolic.
No?
Parabolic.
Parabolic. Parabola just takes you to infinity, and then hyperbola goes to infinity and beyond, wraps around. You have finite A and B for hyperbolas, but they just have negative values now instead of positive values. Good. Great. Great review. So that actually leads into straight what we want to do here. So one of the problems asks you to do a coordinate transformation And there's lots of different types of coordinate transformation that we can do. We're not going to be exhaustive here. I'm going to focus primarily on regular orbit elements, but in projects, I know in years past, people had sometimes wanted to use equinoctial elements. If you've heard of those are non-singular elements, whereas the classical sending node, inclination, argument, periapsis, those things have singularities. Anybody happen to remember where those 313 angles go singular? Steph?
Inclination 90 degrees?
No, not 90. 90 is okay. Yeah, 0 and 180, yep, because it's an actual symmetric sequence, so it's always a 0, and then anyway. So 0 inclination, because then you do ascending node, no inclination, and then argument periapsis. The sum of the angles is good, but the inverse is not well defined, and mathematically things will break down. So there's other coordinates you could use. Of course, the trade-off is now they work for every orbit, but what's the penalty you have to deal with equinoctial orbit elements?
Redundant?
No, they're not redundant, actually. They're still just a 6-parameter set. But, yeah.
I'm not sure, but I want to say that they don't really relate to the physical shape of your orbit like your classical ones do.
Yeah, it's just a mathematical definition. We're adding all these weird angles and doing stuff, so it's harder to interpret, absolutely. And the algebra, if you've seen equinoctial orbits, and things quickly get a lot. And what might take 5 lines to write out now takes maybe 2 pages to write out, all of a sudden. Well, it all works out beautifully. So in code, we don't care. But if you're doing analysis, and in this class we're doing a lot of analysis and analytic predictions of relative motions, and it turns out for what we do, the classical elements are just fine. So that's what I expect you to remember as we go through. If you want to do other ones for the project, that's cool stuff to get into, and I'll show you some other ideas. Thursday, too, I wanted to highlight, I'm going to start talking about the project. One, we still have to think about this. And I'll give some more highlights and what I expect from you to do, because pretty soon you'll be writing me a little proposal of what you will be doing for your first project. And your first project has to be on the kinematics or dynamics of formations. No control yet. The second project will have something that's control-centric, because then we'll have done all the control stuff. But the first part is how to describe formations, how to do the dynamics of formations. And this can be stuff around Earth, stuff around the Moon. This could be flyby orbits, hyperbolic versus elliptic. This can be also around asteroids or other bodies. I've had students do that kind of stuff. If you have any research, if you think, hey, this could actually tie in, fantastic. It's good to make dual use, I don't want you to take one of my papers as a reference, because many students take a paper that they find on the net and go, okay, I want to duplicate these results, maybe add this case and run my own simulations, and that's what I want to study and understand. But I don't want you to use my papers that are actually very related to what we're just doing in class. I want you to do something slightly different, right? Because you find that other papers, other authors, different notations, different ways of talking about it, it'll give you more breadth by doing something like that. So anyway, so you can kind of think about this a little bit if you've seen papers or where you want to go. We'll have more discussions on Thursday on this and in detail. But that is coming up. So what are we doing? We haven't done formations yet, but it's all going to be coming. So you can find a paper up front. Now, classical orbit elements. I have here 6 elements, A, E, I, big omega, little omega, and M naught. As we would define them, A, say major axis, eccentricity, inclination, sending node, argument, periapsis. These first 2 define what of an orbit? Sarah?
The shape.
A shape, essentially, right? How big is it, roughly speaking? Because I want you to think in those terms what these elements mean, because then we go to relative orbit descriptions, we'll have very similar stuff, where we'll want to get practice of what does this impact? How does eccentricity impact my shape and size and dimensions? So this is more shape, this is maybe the size, this is kind of the shape. These 3, what are they? What do they define?
The orientation of the orbit with respect to the planet or body?
Yep. So you have some inertial frame. How is this orbit plane now defined, right? We've proven earlier with momenta that all these orbits, in Keplerian sense at least, are planar. So that defines it. And these are nothing but 313 Euler angles. If you've taken something like attitude dynamics already, you'll recognize those as a 313 sequence of angles. So what is this last angle then? Why do we need that one? Go ahead, Carlos.
To figure out your actual position on it.
Right. That tells you the shape, the size of the orbit, how it's laying in the plane. The last one is to tell you at what time are you at what point in that trajectory, right? That's what's still needed here. Did we have to use mean anomaly? Is there a different angle we could have used? Yeah. True anomaly, right? Eccentric anomaly. We could use all kinds of stuff, or combinations of angles, as you do with equinoctial. This is one set. This is not necessarily unique, but it's handy. I like the mean anomaly just for Kepler's problem, time of flight. I already have the part I need. Somebody's already done that math, and I can now propagate forward more easily. So just depends on how that goes. Now, these are also called invariants of motion. Trevor, why would they be called invariants of motion, these 6 elements?
Well, if they don't change in time.
Exactly. Are there other invariants of motion you can think of? Nicholas?
I would rather say like conservation of energy.
You could use energy, yeah.
Angular momentum.
Angular momentum is a conservation,
Momentum.
right? So we have a differential equation that looks like this. Unperturbed right now. We're just looking at Keplerian motion, right? What order differential equation is this? Jonathan?
Second order.
Pretty simple, right? Second, great. Now, this is not a scalar differential equation. This is a vector differential equation. So, 3-dimensional vector, second order. How many initial conditions are you going to need to be able to solve this?
6.
6. 3 positions, 3 velocities. So if we have x naught, y naught, z naught, and your velocities x dot naught, y naught dot, z naught dot, right? I have 6 coordinates. Are these 6 numbers invariants of motion?
I would say yes.
Yes, actually they are. So you can think of it, if you're looking at this dynamical system, trying to figure out how many invariants of motion, they don't have to be unique quantities, because I can always combine some of them, and get energy out of it, right? So the different transformations you can do on these invariants, but there has to be 6 invariants of motion because there's 6 initial conditions. If I'm on this trajectory, I must have started on this particular point and had this particular velocity. Second order differential equation, then you got a unique thing you can forward integrate, right? So why don't we typically give you the orbits like this for doing analysis? Computer codes love this. They propagate, they go through it, they do all the math, right? But for us, we don't typically use this. Why not, Steph?
Because again, you have sort of the same issue that it's very difficult to see, physically what's going on.
Yeah, it's not as insightful. If I'm giving you same major axis eccentricity, maybe I don't even care what the orbit plane is. I'm trying to figure out how energy it will take to boost that orbit 300 kilometers to get out of the, A train or something. I don't need all this information. I can, it's much, much easier to visualize, see what's going on. So these are nice, these invariants of motion, and we use them a lot. There we go. So we have 6, instead of just, x, y, and z initial, and velocity x, y, and z initial, we actually prefer what's called these elements, sometimes called ephemeris information for an orbit. And unperturbed, these are all constants, right? Which is nice. And again, this is Kepler's equation, essentially. This is where you're solving the difference between your angles, anomaly measure, how it relates to a difference in time. So with this, you can now solve any orbit you wish. I don't have to do a numerical forward integration, because you probably have a nice analytic answer how these anomalies vary, and then you can map it later. And off we go. So this is all 313s and different frames. Now, there's different coordinate frames. I'm just going to define them once. For a lot of the equations of motion, we need inertial ones. So if you're doing motion that are close to the Earth, we use an Earth-centered inertial or an ECI frame. I tend to use this script N as an inertial frame denotation. And IX, IY, IZ. IX, in those ECI frames, tends to point to vernal equinox, which is just a place in the stars. That's a good common reference for everybody. Peripheral frame. This one is defined through IE, IP, IH. IE, actually, as we defined when we derived the eccentricity vector, points towards periapsis, right? It's also one of those invariants of motion. IH is along the momentum axis, so that is perpendicular to your orbit plane. And then IP is just a cross product between them that happens to be your position vector direction when you're at the semilattice rectum length, right? At F equals 90 degrees. So that's IE, IP, IH. And I'm saying here, this is actually inertial, but with the strong assumption that in the absence of perturbations. If we do include perturbations like J2, solar radiation pressure, these orbits may not stay planar, right? With that effect, J2, you can have your orbit plane processing around and doing stuff. In that case, this no longer is an inertial frame. But if we're doing some analysis, assuming unperturbed motion, you could treat perifocal as inertial and actually can simplify some of the stuff that you're doing. The orbit frame, that's the one that tracks the satellite. That's essentially that example one we did in the first day of class on the transport theorem. So the first direction just tracks the satellite's direction. You know, it is 6,000 kilometers that way. Then you still have the same IH, and the cross product of the two gives you I theta. So for a circular orbit, I theta happens to be your velocity direction. For an elliptic orbit, not generally, unless you have periapsis or apoapsis. But otherwise, you'd have a radial rate and a tangential rate, right? But that's the 2-1. And the orbit frame is always rotating. And you're doing here. You do this. So, any question on the coordinate frames? We've discussed this a little bit earlier. Here's a picture trying to illustrate that. So, if we're trying to solve our positions, there's many ways we can do this. If we use the perifocal frame, the nice thing about the perifocal frame is you can just write everything out. You know, you can look down. Let me just draw this out. But in the perifocal frame, you know, you got your major axis, your minor. Let's see if I can draw a reasonable. Well, that's an awful. Come on. Okay. Still bad, but a little bit better. Okay, so if you have your periapsis, your apoapsis, this is your focal point. With the perifocal frame, we've picked a frame where this is your first axis, i.e., that's your second axis, IP, then IH comes out of the paper. So it's nice, no matter what the plane orientation, I can always line up your paper such that you can draw it undistorted. That's kind of nice. Then if you have a certain position, R vector, we can break it down into X in this direction and Y in that direction. This is your true anomaly angle F, and then if you know your current radius, we found X just to be R times cosine F, and then Y was R times sine F, right? That's all we're doing here. In a vector form, if you write these things out, that's X in the IE direction, Y in the IP direction, and representing these vectors now as a matrix, right? With P frame components, this left superscript P is important. It's simply X, Y, and 0. So if you solve time of flight, you know all the orbit elements. How do I get R at a later time? You have all the orbit elements at your disposal. What equation would you use to find your orbit radius? Nicholas?
Obligatory equation, where you have h squared divided by mu over 1 plus c.
Or also the p over 1 plus e cosine f, right? Different ways to write it. Yep, but you can get from A and E, you can get p, you got e down there. Sometimes you get the true anomaly, and with Kepler, you know, with the translation from m to big E to f or back and forth, it's all given. You can do that. So I can get my r. If I know f, I can do my cosines and sines. I can get an x and y. I can get now the x, y, you know, my position vector of that satellite, but it's relative to this frame. What you want for your computer codes typically when you're doing visualization, where these orbits relative to Earth, over what place of the Earth am I right now, you want to map everything back to the ECI frame. So how do we do that? Well, what we want to have is this. We want the x, I'm using capital X, Y, and Z to denote inertial coordinates versus small x, which is perifocal coordinates. I want to figure out how do I go from here to here. And if you've done anything with, has anybody here not used the rotation matrix to translate between two coordinate frames? Vector components. You've done that before. So that's essentially what we're doing. Different ways to write a notation matrix. Some have an R, some have a T, some have superscripts, subscripts, different letter combinations, just different notations out there. What I use here, and what you'll see in the book, is a two-letter notation where I have a direction cosine matrix NP, and these things always go from right to left. That means you're mapping something with vector components in the P frame into the same vector expressed in N frame components. So we need to figure out what is this NP rotation matrix, and then you just have to multiply it out. So what is NP going to depend on? Nick?
Your three orientation angles.
Exactly. So if you go look at how is the orientation of the P frame related to the N frame, and in fact we have to do this first, a 3-axis ascending node rotation, then we do the 1-axis inclination one, and then you do another little omega rotation in that right plane to get you lined up. Now that puts your first axis from here, goes to here, then it rotates, and it goes up to here. That becomes IE. So that's the basically 313 angles you would use. And that gives you this matrix. Well, good. So just one slide for review. If you haven't seen too much of rotation, 5010 in the spring covers this in great detail. This is all you need for this class, knowing how to go to and from this stuff. So these rotation matrices tend to be orthogonal. If you hear orthogonal, you should think what? Trevor?
Or with perpendicular basis.
They have a perpendicular basis. That by itself doesn't necessarily make them orthogonal. But if a matrix is orthogonal, what's the nice property you're going to have?
Inverse is its transpose.
Inverse is the transpose, essentially, what you're seeing here. So that's really nice. Because even a 3x3 matrix, analytically, you can do it, but it takes quite a bit of paper already. If in your analysis, all you have to do is change that inverse with the transpose, man, your life becomes so much easier. So the rotation, if I know how to go from the inertial to the P frame, and I need one that goes from the P frame to the inertial, you'd have to invert it, or in this case, just transpose it. All right? You shouldn't have anywhere in your code an inverse of a 3x3 orthogonal matrix. Just put a transpose in there. How do we get there? It's a 3-1-3 sequence, so you can look up your standard Euler angle addition sequences. We're doing first a 3 rotation about the current 3 axis. Then we're doing the 1 rotation about the current 1. And then another 3, because now we've shifted into the right orbit plane. Now we have to do another 3-axis rotation to line up our first axis with the direction of the periapsis. And that's the sequence. If you carry out the matrix math, this is the formula. This is essentially what you need for the code if you want to program this. If you have the 3 angles, you just plug your stuff in, and then out comes NP. So it goes from the N frame to the P frame. If you wanted the opposite, like we did on the other slide, you would simply transpose this result. If you're going backwards, if somebody gives you this stuff, and you will find this in information flying, when we have the chief orbit position and velocity, and that's the chief LVLH frame and whatever hill frame, whatever they call it, and we're trying to figure out what are those angles associated with it, you might have to go backwards. And the way you do that is you can find the second angle is always easy. It's either the inverse cosine or sine. Because it's a symmetric sequence, here it ends up being an inverse cosine, which gives you an angle between what range of numbers? An inverse cosine. Me here. Remember?
0 and 180.
0 and 180, right? So classically, you'd never have a minus 10 degree inclination defined in orbits. That's actually defined to be between 0 and 180, and you can get all that range. So good, because it's always, because big omega is where you ascend. Because if you otherwise, if you used, instead of this angle, you could, this line of nodes, you could extend backwards, right? If big omega were defined here where the orbit descends, you would end up having weird different, negative inclination angles. Then you might be using a descending node instead of ascending node. So this is the ascending part, the part where your orbit plane ascends upwards as defined by the ECI frame. Okay, so good, that one's easy. Big omega, little omega, we take ratios of 2 of these components and then take an inverse tangent. So, seems simple. There's always a few little errors with the best of intentions that can happen here. One, what in your MATLAB or C code, which A tan function are you going to use? Josh? A tan2. You need to take 2 arguments. Why? Well, big omega and little omega are defined over what range? It's not just 0 to 80, but
0 to 90.
no, bigger.
Negative 90, 90.
Even bigger.
0 to pi.
There we go. Everywhere. Okay? Because if you look at the descending node, you could this orbit plane could punch through the equatorial plane really at any orientation there. So it could be between plus minus 180, 0 to 360, whatever you want to call it. But you need all 4 quadrants. And the regular A tan function will not give you that. It only gives you 2 quadrants. So we need to have 4. And this is where it gets tricky. I know in Europe we do 1, 2, 3, 4. The US, anyway, it's different. I mean 4 quadrants, not weird stuff. Now, the other thing is, with these arguments, I have a minus sign here. Could I just take the minus sign on top or take it outside of the A tan function? Joanna?
No.
Why?
Because in MATLAB, you put the x and the y separately.
Right. So this is your y over x, and whatever this number is, if this is 0.3, then you have to put in minus 0.3. If this is minus 0.2, then minus gives you a positive 0.2, right? But it gives you the right quadrant by having, okay, my x, I'm going to be on the positive x side or the negative x side. You can't, if in a regular A-tan function, it's an odd function and you can just take it outside and it doesn't change anything. A-tan 2, it will change stuff. Keep that minus sign where it is. Okay, don't get smart. Okay, same thing here. Good, so we've seen the basic rotation matrix. We've quickly reviewed how to go back and forth. So now, this is essentially one of your codes there. How do we go? I have all these orbit elements, and the anomaly angle, I've already done the math. Going from eccentric or true anomaly, it's easy to straightforward to go to mean anomaly. I've already got that. I have a time of flight. I now wish to figure out where will I be in 3 hours, or where was this object 2 hours ago, right? How do I do that? Because everything's given an invariance, it's nice. Nothing changes with time as far as these are concerned, right? What does change with time, of course, is your mean anomaly angle itself. And this is your Kepler's equation again, time of flight. So we have a current one plus, what do we call this quantity? Square root mu over a cubed?
Mean motion.
That's your mean rate, right? It's your mean orbit rate that you'd have. That would be a little n. I would use it if I typically have that defined. So times your time of flight that you're considering, forwards or backwards, that gives you this. Now we have to solve Kepler's equation. That means m to e to f. Which step here do you have to use a numerical iterator? Eric?
Between E and F. Or no, M and E.
M and E, yeah, from M to E. There, E to M, it's just, you can actually plug in numbers. M to E, you have to iterate a few times. That's it, exactly. And then from here on, it's no quadrant issues. You can use the standard A-tan functions again, and you get there. So now that we've found the new anomaly we have, we get either E or F. I've chosen to go to F, but I've shown you actually X, Y, and Z coordinates. They're in Chapter 9 in terms of eccentric anomaly, so you could use those as well to get X, Y, and Z. I'm just using the ones in terms of F. You will find just a little bit down the road, we don't need theta here. This is called the true latitude. It's the argument periapsis plus F. This is handy. Geometrically, what does this angle then mean, theta? If you look at the picture. Right, because you can see ascending node, inclination. Then we have to rotate so far in the orbit plane just to get the periapsis. And then we have another angle, F, which is a true anomaly.
Isn't it the angle from the equatorial plane?
Yep. Measured within the orbit plane, right? So you've gone this 3 rotation, now we're doing a 1. This is my new orbit plane. I have to rotate 20 degrees just to get this line up at periapsis. And then relative to periapsis, I've already flown 30 degrees. So it's 20, it's all a rotation in the same plane. So it's, your position is actually now 50 degrees since you crossed the equator. So that's what they call the true latitude. And we'll see that angle appear several times also in formation flying descriptions. So anyway, so now we have F. I can use my radius equation we discussed earlier. So from A and E, I can compute P. I think that was A times square root 1 minus E squared, I think. I have to go look it up. Plus 1 plus E cosine F. The X and Y coordinates is just the radius times cosine F, sine F. This will give you all the right stuff. Now, I also need this rotation matrix, because we want to then go from P to N. And so I'm using my standard. All these DCMs in the book are defined from the inertial frame to the new frame. If you go look up formulas in a computer science book, it'll do it just backwards. Because in computer science, they love to do everything back into the inertial frame for gaming, putting everything together, and all these kind of cool things. Fantastic. So all the definitions are just a transpose of what we have. But in robotics, no, robotics actually does it backwards too. We're doing it the right way. We're going forwards. So for us, just make sure, if you use other texts and look it up and you find, wait, everything's weirdly transposed, some groups do that, But for us, we're always going from the inertial one when you're doing the 3-1-3 rotation, that's to that one. What we need is we have the position now in the P frame, so I need to go backwards to the N frame. So I take this Pn, and instead of inverting it, I transpose it. It's an orthogonal matrix, right? And that's it. Now you've got everything you need to get this position vector. It's an easy way to go from orbit elements to my inertial position vector, solve it there. And there's different ways this can be done, but that's handy. Here's the full thing. So here I'm showing you now same expression in terms of all the orbit elements. I've solved for F, so I can get R, I can plug it everything in, and then this is the answer you would get. But instead of using little omega and f, actually there's some trig identities you can use, and you end up just having theta in there. And so that earlier angle you saw defined would give you straight away this r vector. Now, how do we find this? This is a good practice of the stuff. So if I have IE, IP, right, and we've got some elliptic orbit. So there's F, R, and we're doing these things. Now, I was expressing R in terms of the perifocal frame and then rotating from the perifocal frame components into inertial to get what I'm finally after. What if I choose to express R in the orbit frame? What is R defined as? Something in orbit frame components. What do you think, Sam?
R00.
R00. It's very simple as well. But now, if you want to get this in the inertial frame components, and I have it easily in the O frame components, Sam, which rotation matrix would I need?
To get it in the O.
You have it in O, I want it in N. So we use a rotation matrix, and I'm using a two-letter notation. So NO or ON, if you feel lucky.
You want it in N, so you need NO.
NO, that's it. Yep. So when you write these things out with this two-letter notation, if this is in the O frame, what comes next to it better be in the O frame, because it has to map something from the O frame to whatever else. If you find these things not being adjacent, that should be a big warning bell. And it's one of the nice things why I like this notation so much. It's less to get confused with the superscript, subscript sometimes. I'm never sure how they quite define that, and this is just a little bit easier. So that's it. And that's literally what you could do. So now we used the 313, big omega I, little omega, to get from N to the P frame. What angles do we have to use to get from N to the O frame? If you had 50-10, this probably would be easier. I'll just see who can venture a guess. So I need NO, and NO will be defined in terms of three angles. Go ahead.
You will need the right ascension of the sending node.
Okay, still big omega.
Your inclination.
Inclination.
And what we call theta.
And then the theta angle, right? So if we go back and look at this picture, this will hopefully make sense. Because we still, to go from the inertial frame, I have to rotate big omega to line up my first axis with the nodes. Then I'm rotating about my current one axis by the inclination. Then I did that little omega that gets me here. Now I need to have my first axis point at the spacecraft, right? So I need to do the additional, but it's about the same three. So it's still a 3-1-3 axis. It's the same math I just showed you, but instead of plugging in little omega in that math you saw on the other slide, you plug in theta. Because the last three-axis rotation is going to be theta, not that. That gets you there. And that's it. So that's another way. So it's good to kind of, well, no, I need to go back to my slides. So it's good to go back and forth different ways. So that you can get this. The same thing now with the velocity vector directions. This is a planar motion. So if we know R, that's the position, great. So, we said R was R times IR, right? The inertial velocity we've already derived several times in class using the transport theorem. And you differentiated this, get the inertial derivative, you get a radial rate times this plus R times F dot times I theta, right? That was your inertial velocity. This is the polar coordinate example. I've just used now conveniently this rotating stuff, so everything's really simple, but it applies generally to orbits. So how do we go? This is now my inertial velocity expressed in O-frame components. How do I go from here back to this? Well, there we go, she's slow. Okay, to this expression. This is the inertial velocity expressed in N-frame components. Well, the O-frame components, using the rotation matrix, I need an ON rotation matrix to go from O to N. We'll get you there. You notice, though, in here, there's no F dot. There's a mu appearing and an H appearing. And the H is kind of a dead giveaway. We've seen one of those as astro identities that the angular momentum magnitude was R times F dot squared, I believe. one of those formulas. So they'd use some substitutions here to get it into this particular form. You don't have to solve for the actual rate. It comes out of this stuff. So with angular momentum, if I know my radius on the orbit, I can always compute how fast the angular rate has to be because of conservation of momentum. That's what was used. So no black magic. It's just, it found easy ways to express it in the orbit frame, and then you have to be comfortable to map this stuff back to the inertial. A few little astro identities you plugged in, and then that's where it came from. So whatever you want to code in your stuff is up to you. Just showing you different ways to do it. Now, the other way around, out of code, in particularly, or observations, you might be getting stuff that directly says, hey, I measured with a radar and actually did all the transformations and coordinate frame math. This was the inertial position, and we tracked it, and we actually got some velocity. Now I'm trying to figure out what are the orbit elements of that object, piece of space debris that we just tracked, right? And these are all inertial vectors with inertial rates that we're looking at here. So how do we do the inverse problem? So in your code, when you're testing it, what should you do with your subroutines? You start out with elements, you get Cartesian. When you're testing this next one, which Cartesian should you probably throw into that subroutine?
The one you just got.
Exactly. Why?
Because you know
what the answer should be, hopefully, right? You want to be able to go back and forth without this stuff getting corrupted, right? It's a good example. So how do we make sure, now, if we did the earlier math correctly, if I put in those Cartesian position velocity, I should get back to, say, more of the elements. Well, I'm kind of outlining some of the math here. Again, different ways to do this stuff. But from the Cartesian position vector, your current radius is simply the magnitude, the sum squared of all the components. So that's r dotted with itself. The dot product gives you the magnitude squared. Take the square root. Off you go. Same thing with the velocity squared at that instant. It would be the velocity vector. So you get the components squared. And I'm not taking a square root because I'm looking for v naught squared. If I want to get the angular momentum vector, I have r crossed r dot. Well, here r and r dot are given an inertial frame component, so I can compute h. It's just going to be, some big number in that direction relative to inertial frame. It's not relative to an orbit frame right now. But from that, I can get the magnitude by taking a dot of h with itself, take the square root, you get the magnitude of the vector, and now I have h. Why is that handy all of a sudden, h? With h, what can you get quickly?
Inclination.
Sorry?
Inclination.
H magnitude, sorry. You're right, down with the h vector, it'll help towards inclination. But the h magnitude, what does it relate to? I'm trying to make sure you guys are kind of more comfortable with these orbit identities.
Semi-major axis.
Not quite. We still need eccentricity to do that. What's the other parameter? The radius equation that Nicholas was talking about earlier. He was talking about r is equal to mu over square root of, yeah.
Over 1 plus c.
Right. So the magnitude of h was simply square root of mu times p that you've had there. So since you know what mu is, we know what planet we're orbiting about, hopefully. We can get your semi-latus rectum out of that thing directly, right? So one of the elements comes out of it very quickly. So anyway, so these are all convenient things to have. Now, we're still looking for the classical elements, A, E, I, big omega, little omega, and mean anomaly. So this doesn't give us the answer yet, it just kind of sets things up. To get A, as Lauren was talking about, we're going to use energy equation. This will tell us what type of orbit we have uniquely, right? Eccentricity, what was the issue, Sarah? If I would compute my eccentricity, why would I not know what type of orbit I have?
Because you have the rectilinear motion.
Exactly. Or you might have something very close to, E is equal to 1 if something's coming into the Earth, could give you all kinds of issues. You compute this. If A goes to infinity, you simply compute an energy level of 0, and you know right away, woo, I better be careful and use some other equations to solve time of flight and so forth. In this class, you won't have that, but you might as well write your code generically. So this is my energy equation, slightly rewritten, where I'm just solving for 1 over A for the orbit side. I have R, I have V, right, that I can plug in, and I know what mu is. With this, you will have your A. And hopefully it's positive, then it's elliptic orbit, bounded, and you just invert it, and you get your A out of this stuff. Nice. So we already got one of our elements. The other one, with the momentum vector, the eccentricity vector was defined like this. The velocity cross momentum divided by mu minus your IR, your radius, your unit direction vector of the position vector. And that gives you the eccentricity, and we defined eccentricity then to be the norm of that. So if you have a circular orbit, this will still work. It'll just give you an E of 0. If you have rectilinear, it's going to give you an E of 1. It's still going to work with all this math. So this is nice and universal, a way to get your eccentricity. So we're down to A and E. What's the next set we're going to need? So A is shape, A is size, E is shape. The next three, orientation, right? How do we get all this stuff? And that's where we need the vector to get inclination, as what you're talking about, Eric. Exactly. So how do we get this? I'm going to use this definition. If you can look it up in chapter 3. If you haven't taken 5010 yet and seen some of these transformations, no big deal, just trust it. If you want to look it up in chapter 3, it goes through the details. But it turns out, going from the inertial frame to the P frame, if you just take the P frame axes, i.e. IP, IH, and they're expressed in n frame components, so it says IE is in this direction, IP is here, and IH is there, and everything's expressed in n-frame components. You make just each, 3 by 1, 3 by 1, 3 by 1, it gives you a 3 by 3. That is your rotation matrix, or DCM, direction cosine matrix. So that's a handy formula. That's all you need to know. If you haven't seen the rest, that's a little bit fuzzy. Doesn't matter for this class. So with this, so how do I get these unit direction vectors? Well, I've already had E. I found the magnitude. I can normalize it. I have H. I found the magnitude of H vector, so I can normalize it. That gives you IH. And then IP has to be, because it's a right-handed orthogonal coordinate system, you got IH crossed IE gives you IP. That's basically the math you'll do. Now, where will you run into issues here with this formula?
When E is equal to 0.
So if E is equal to 0, I have something over E. Could you use L'Hopital's rule to find what IE still is here? You've heard of L'Hopital's rule? So you have 0 over 0. I know, it's been long for me. Even longer, I bet. But you have these 0 over 0 issues in a calculus class, and is there an actual limit? And sometimes there is. If you have something finite over 0, no way, it blows up, right? But 0 over 0, maybe, maybe not. And you take derivatives of the numerator, denominator, and evaluate it at 0, and at some point it goes away from 0, 0 to either something over 0, which means it blows up, or it's 0 over something, which means it goes to 0, or it gives you a finite number. Could we use that here? What do you think, Joanna? So think of fundamentally what IE is, and we're on a circular orbit. Is there a distinct IE answer? That's what L'Hopital's rule would provide you, right? Is IE defined for a circular orbit?
Yeah? No?
But there are two options. Which ones are you picking?
Oh, I don't know.
So what is IE? Where does it point in space?
Periapse.
Periapsis. Periapsis means what?
The closest point.
So in a circle, which points in a circle is the closest point?
All of them.
So is there a unique IE direction?
I suppose not.
No. Have confidence. Come on. That's right. You want to argue with me here. Okay. So say no. That makes sense because you should not have that. So L'Hopital's rules, even if you try to apply it from the geometry up front, we should be able to argue this cannot. We know for a circular orbit, IE is not defined, and it would drop out. So when you compute these things and you get an E of 0, you might want to check in your code and just go, well, if E is really zeroed within machine precision, where do you set IE then? You just have the code blow up? What do you do?
Usually use the theta angle, I guess.
Well, yeah, but if you want to get classical elements, I am looking for these complete transformations. That means I will need this part to figure out what my little omega is.
Yeah.
Because from this DCM, I will extract with the A tangent and the A cosines some angles.
But little omega would be undefined.
So what do you do?
I usually set it to be equal to 0, and
If you want it. Exactly. So since it doesn't matter, every point is the closest in your code. There's nothing wrong with just saying, I'm making it 0 just because it's an easy number. I can make it 56.79 degrees. It doesn't matter. But then you have to be consistent, right? Because if you set it to 0 and your satellite is here, that might be about 45 degrees. If you set it initially to 20, well, then F has to be 25 degrees, right, relative to period. So otherwise your time of flight is going to be off. So this you can get around in classical elements. If it's really, really close to 0, you can set it to any number, as long as you're consistent. then it works. So for elliptic orbits and everything that we're doing here, do you have distinct IE/IP? IH for a circular orbit, is that still well defined? Yeah, no problem. You have an orbit plane and circular orbit, it has a normal. This one will be not as much defined, but if you're doing this stuff and you're inverting it, and I've plugged in the components that I would need of this matrix, it turns out you're going to need elements here of the third row. This will be affected by IE, and this is where you're not going to have a nice answer that's going to work out, because it's not defined. But big omega and I are still defined for a general, at least assuming a non-zero inclination. Otherwise, you'd have issues here as well. If you have an equatorial orbit, then you're never punching through the equatorial plane, but you're in the plane, right? So your ascending node is not defined. So again, you could pick any number, and as long as you're consistent, it works. But anyway, but this is it. So you can plug in, get your direction cosine from the inertial to perifocal, use your standard math, and this extracts now the 3 orientation angles we need to go from inertial to that frame. All right, those are the 3 angles. Good. The last one we need is what? We have size, shape, and orientation of the orbit.
Your location.
Where are you at this time? And again, this is at all position velocity at a particular time. And I'm showing you here a formula how from these vectors you can compute this. So let me, before you stare at that too much, so if you're doing these things here, we said, okay, so we've got this. If this is IR, this is I theta, right? And I'm looking for F. Couldn't I just say, well, IR dotted with I theta is going to be equal to what?
Why I theta? Should be IE.
There you go. Thank you. IE. So with the, let me get rid of this minus sign. But it's IR and IE. If you take a dot product between 2 unit direction vectors, what do you get? Cosine of the angle between them, which is just cosine F. Couldn't you just use this? It looks simpler. Do an inverse cosine, do a dot product, get 0.3, do an inverse cosine, and get an angle of 60 degrees, or whatever the answer happens to be. Why not? What's the issue with this one?
It would be ambiguous if you were
Right?
past 180.
This would work here. So if you have your nice ellipse, this works here, it works here, it works here, it works here. But Sam claims as I get past 180, I'd have issues. So if you see your plots, you're doing this stuff, and you're plotting out your orbits, and everything works fine, you definitely want to look at all 4 quadrants. Don't just check your first, because a lot of bugs could be in there where it looks good for one, but then, because what will happen in your orbits is you're doing stuff, and all of a sudden the wormhole appears, and your orbit jumps back to over here in space, and then it plots kind of only half orbits at a time. You're not finding, wormholes in space. What you're just doing is some trig errors. You have to have F defined over 4 quadrants, and cosine of that will simply give it to you over 2 quadrants, not all 4. Well, then we go, okay, great. So I could use let me just do, if I do IE crossed with IR, what will that give me? It will give me, the magnitude of this times the magnitude of the other times sine of the angle, times a direction. A cross product gives you a direction, right? And that will be simply perpendicular to the orbit plane, so it's IH. This will give me a sine F. Great, but that's not defined over all 4 quadrants either, also only 2. So how do we find one that works over all 4? We tend to use the atan 2 function, right, with 2 arguments. And that's where this one came from. So I'm not saying this is the only way to compute these things, but this is basically my sine term, and I'm dotting with H to make it a magnitude, of, that's the thing you need. And then I have an IE over IR, which is the cosine, and you do the ratios, and out comes F. So a little bit extra math, but you have all these quantities by computing these other things earlier, and this will drop out just fine. So if you pick the small angle of 0, you still need to make sure you have a corresponding IE angle that makes sense. Right? because otherwise all this will break apart and it will not make sense. So you need to have a consistent, if you picked a certain angle there, that has, if little omega is in, if it's 0, then this IE direction has to be basically your line of nodes that you've computed in space. That's what you're setting it to. So just make sure it's consistent. Again, more generalities in this class. We're not going to worry too much about some of these edge cases, but just, you know, it's a good warm-up. Any questions on these transformations that we were doing? Obviously, I want you to do this, but the goal here is not just, hey, can I do some basic astro identities and back and forth, but you will see for relative orbit descriptions, we'll spend quite a bit of time on kinematics, which is just going from one set of coordinates to another. How can you describe relative orbits? And there's different ways to do this that it makes life easier. And then when you have one set of coordinates, you always need to be able to translate to other set of coordinates and back and forth. So the similar stuff what you're practicing here in the inertial, things you've hopefully seen at some point, in some way, we will be doing a little bit more complicated looking math for the relative formations. Eric.
On the homework, is it okay if we do things a little differently, like if we use eigenaxes and quaternions instead of DCMs?
You can. To go from that, there's lots of different ways to go from those two orientations and break it down into those 313 angles. Yeah, but you just need to go to the 313 angles. Yep. Yep, absolutely. I'm just showing you one way. If you have other ways to do some of these other formulas, that lots of different formulas that exist. But conceptually, it should be similar steps that you're putting in there. Okay, good. Last topic I want to go through is, I'm just curious, does anybody know what I mean by Lagrange Gibbs F and G solution for classical two-body problem? We've done where am I now, where am I later, right? I can solve it numerically by solving the differential equation, or I can do it analytically by just knowing Kepler's equation and everything's in a plane and know the orbit elements and I can get there. The F and G does it slightly differently. Have anybody seen this? Carlos?
I think so.
You think so?
So some of F and G functions, so I'm...
Right?
We covered it in 50-50 last year.
Good. Okay, so you will see it there. So some of you taking 50-50 now, you'll see more of this. I just want to review quickly. It's another way to solve time-of-flight problems. It's just a way to get into the stuff. Relative motion, we won't be using F and G. But what I want to highlight is, I don't think I've ever seen a paper do relative motion in terms of F and G. It might be something. And I think this might only work for the circular chief case, because then the relative motion would still be planar. Because this is all hinging on the motion that you care about being planar. But the functions have to vary, and who knows how that works. Might make a good project, so for somebody. But another thing is just to show there's lots of stuff out there. And I've cut out some of the developments. We're going to go through some highlights. This is actually in the book as well. But the interesting thing is, I want a nice analytic answer, and my elements allow me to do that. I have AE, big omega I, and everything else. I get my mean rate. I know where I am. I can forward propagate where I am, you know. But then you have to do all this math to go backwards and get your Cartesian coordinates. Because if you're plotting, or you want to compute, hey, is this space debris going to have a conjunction with this thing here? Or you have a servicer orbiting about a broken satellite. Are you going to have a trajectory that's going to crash? And just looking at elements, it's actually difficult. It's easier in Cartesian coordinates to go, whoa, they're getting really close, right? So there's different reasons why people like actually Cartesians as well. It's good to be able to do both. The F and G solution tends to be a hybrid answer, where instead of using the 6 invariants, which are A, E, I, big omega, little omega, and M naught, they just use initial position, initial inertial velocity. We argued earlier, those have to be invariants as well, right? And we know how to go back and forth, Cartesian to elements, elements to Cartesian. So they use those, and now the next thing they're taking advantage of is the fact that all orbits, unperturbed, are planar. Now, assuming we're not doing rectilinear motion, your position vector and your velocity vector span the orbit plane. Right? And if you go done basic linear algebra, if two vectors span the orbit, that plane, and all resulting vectors of position and velocity have to be in that plane, that means you can always write the position at any time as a linear combination of these two initial vectors. Purely vector algebra, right? That's kind of where it's coming from. Can we do that? And so it turns out these F and G's can't be constant. That wouldn't make sense. Otherwise you always get the same answer. So they have to vary with time. And we can write these F and G's later on in terms of orbit elements. And you can solve Kepler's equation. And so we can use the elements to quickly figure out what is F, what is G, and F dot and G dot. But then I just simply use that as scalar multipliers to figure out then, you know, this much times R naught, this times R naught dot, and that'll tell me this is where the new vector is. Yes, Nicholas?
Does it work with the rectilinear motion? Because in that case, they would be kind of like linearly dependent.
Rectilinear motion just would not work. You'd have to, it's not spanning the plane. Well, I haven't looked at it in detail. It might work if the right angles are chosen. In angles that work with rectilinear, true anomaly would not work. Because true anomaly is either 0 or 180, regardless of position. So I cannot get unique positions out of it. Rectilinear motion will work with eccentric anomaly. You can solve time of flight problems that way if you're coming in and going out. But because with rectilinear motion, I don't need a plane of answers. If they're all in 1D, then this fundamentally might still work. Because the answer always, if you're pointing up and the velocity is pointing up or down, the answer afterwards always has to be in that same axis. So this might still work. I just haven't tested it, really. But it's a good question, right? But the rectilinear, everything moves to 1D space. I need to make sure my base vectors span 1D space, and they do. But there might be other issues I haven't thought of, so I don't know. But that's basically it. So if I have the f and g functions, I could just, as long as I can compute these easily, these position and velocity become your base functions, but they're not an orthogonal set, unless what is true for your orbit. For what type of orbit do R0 and R0 dots become an orthogonal set? Trevor? Circular orbit, right? Because then your velocity is orthogonal to position always. But for elliptic orbits, not generally the case, except for which points? Periapsis and apoapsis, right? That's where your velocity is orthogonal to your position vector. So you can kind of see some of the influences. To get your velocity, the inertial velocity, I'm simply going to differentiate this relationship. These are scalars. R0, does it vary inertially? It's a fixed set of numbers, right? 50 kilometers, 300 kilometers, 6,000 kilometers, whatever you have. So there's no R0 dot here all of a sudden in chain rules. These are just fixed quantities. But your f and g functions will vary with time, and they will appear in there. So we have to have solutions that give you that. And the initial conditions you can see here, at initial time, this has to give you R0. So f has to be 1, g has to be 0. At initial time, this answer has to be this velocity. So this has to be 1, and this has to be 0. Generally. So that's written here. With a bunch of math, you can prove this constraint equation that these are not linearly independent. These three, this f and g and the rate functions are not all independent. You actually have this constraint on top of it. F times g dot minus g times f dot has to be equal to 1. Outlined a little bit more in the book. So how do we actually do this? There's different ways you can solve for this. One way is numerical. You could find people have investigated this stuff and say, okay, I know my basic equations of motion are given this way. And it turns out, and I'll show my hand here how we come up with these, you can come up with second-order differential equations for f. So given initial conditions for f and f dot that we have, I can now solve for this explicitly. I still need to know what r is versus time, so I could use my elements and those analytic answers to get that. But you could numerically solve for this. So I just want to show this once. How do we get that? This is a fairly short derivation. So we have r double dot minus mu over r cubed times position vector. And we have this new form of a solution where we have f times r naught plus g times the inertial velocity. My inertial velocity is a derivative of that, so it's f dot and g dot times the same base vectors. Here, to plug this in, I can plug in my r, easy. How do I get my r double dot?
Differentiate again.
Just differentiate again. Add another dot everywhere. So I'm just going to be lazy and do it this way. That's it. Again, these things are still there. Sometimes students make this way more complicated than it needs to be. But that's it. So now we have this postulated answer. This has to be true, again, because it's not rectilinear at least, so these things span a plane. This can always be written as a linear combination of the first two vectors. It's an orthogonal basis. You can differentiate it twice. This has to still be true. And now we can plug this in and plug that in. So now if you do this, let's see, what do we get? On the one side, we get f double dot r naught plus g double dot the initial velocity equal to minus mu over r cubed times F initial position minus mu over r cubed g times initial velocity. Now, how can we proceed? The trick here is we can actually combine the initial positions and velocity terms. So you end up with F double dot plus mu over r cubed F times initial position plus g double dot plus mu over r cubed g initial velocity. This thing has to be 0. Now, on the other slide, I claimed this term was actually 0. And that's how we got that differential equation. And this term was 0. Why can I claim this? Nicholas?
Because your assumption is that R naught and R naught dot are linearly independent.
No, linear independent would mean orthogonal.
Not necessarily.
If they're linearly, if they're not orthogonal, then all of a sudden these two vectors would be, there would be some dependency between the directions. You're on the right track. It's all about these vectors, right? So I'm arguing this and this have to individually go to 0 for this to be true. You can try a counter argument and go, well, could the opposite, could this be non-zero and this be non-zero? And then you'd have to be able to add them up. Steph?
But then that would mean that your direction vector and your velocity vector are in the same direction. No?
Yeah, well, so if this is non-zero, this is non-zero, then if these are not in the same direction, there's no way you can make these things match up with space, right? That's one way. It relates to, I said, you were definitely right on the right track. I think the statement was slightly...
But can't you have like bases of not orthogonal vectors?
You can have yes.
So for having a basis, you need to have linearly independent vectors. So if a basis is not orthogonal...
You may be right.
Okay, no.
It's not going to impact the rest, but just for the sake of time. But the key is, if this is, but could you then, anyway, there's weird combinations you can look at. But in the end, sometimes if you have math, this is the easiest way to argue this. If I have, let's go right here, I have some terms times A plus something else times B. You know, forget base vectors and direct, make it a scalar, right? And this has to be true for arbitrary A and arbitrary B. Because I want this relationship to work for any orbit type, not just a particular one where this math, because otherwise I can pick conditions where this is non-zero and this is non-zero. Then I have to solve for a corresponding A to B relationship to make it work. With these vectors, yes, it generally may not work. Special cases it might work, right? But the key argument here is these have to hold for arbitrary initial. I can put my orbit anywhere I want, and it cannot be constrained to only be in 90-degree inclinations or something weird, off you go. So therefore, these things have to individually vanish as well. So many different types of arguments you could argue here. But essentially what comes out of this then is you have these nice, beautiful, simple differential equations that, hopefully, here we go, get to it. Look a lot like the original one, but this is how these F's and G's evolve. So you could propagate there. Good. Now, to find these things, I just want to wrap this up. I'm not going to go through the details here in class. You do it 50-50, but I wanted to highlight it, just different ways to solve for these motions, because we can do similar problems or ideas at least in a relative motion sense afterwards. So if I'm trying to solve this, I need to come up with answers for F and G. And one way to do this is you can look, okay, the perifocal frame, it's convenient because I can just break down X and Y. I have no Z component in the perifocal frame, right? The velocity is going to be X dot, Y dot, and you can actually find analytic answers for these. So therefore, this is your F and G solution written in the perifocal frame. I only have X and Y components, and it's the linear combination of the initial position and the initial X coordinate and the initial X coordinate rate with F and G. Same thing for Y. You can rearrange this math now, put these X, Y, X dot, Y dot in the matrix, right? And you got this. Now, I can take this F and G and typically invert this matrix, and now I can solve for those explicitly. So if you have an analytic answer for the x and y evolutions and the rate evolutions, I can plug it in, and this is now the analytic answer for f and g. And there's all kinds of answers to this. What I tend to use here is eccentric anomaly expressions to express this stuff. In the book, you'll also find ones in terms of true anomaly expressions as well. Different formulas that people have used how to write this. This part here, you can look at momentum and then in perifocal frame and do these cross products and quickly prove to yourself this is nothing but the angular momentum magnitude. So that can be figured out pretty easily from initial conditions. And plugging that in, this is my f and g. So if I have answers for these coordinates analytically, I can find these. You still need to find the rates, which comes in as a derivative of that. So if you solve these kinds of problems, this is what the answers tend to look like. Instead of using actual eccentric anomaly to define where everything is, I have my initial position and velocity and initial time, and now where is it 6 hours later? I'm solving everything in terms of eccentric anomaly difference. So that's what that E hat is, or an H hat. This is for a hyperbolic case. All right? So how much have you moved since then? If you do it in true anomaly, all I know is here, and this is velocity, and then 3 hours later, this vector has rotated 30 degrees. I never have to map it back to an inertial frame to do this by having this difference description, which is nice. So again, this takes many pages of algebra to solve this. I'm not going to do this here. You do this in other classes, obviously. But you can get to F and E. I have A. So given initial conditions, we know from position, velocity, energy equation, I can get A, right? I can get my current radius initially. I have that pretty much given. There's this sigma, which is defined, where's that one? Here, down here, a little odd variable, but it appears a bunch in these orbits. But given initial conditions, I can figure out, I have my position velocity, I can compute that. Let's see, so you got your F, your G, your F dot function. You can see I need my initial radius, no problem from initial conditions. I need my radius at a later time. So now I need to solve something like my radius equation. R is equal to P of 1 plus E cosine F. And you go, whoa, wait, F is defined relative to periapsis. I don't want to use F, I'd rather use, or E, I want to use F hat, right, the differences. So this is a modified version of that. Again, bunch of algebra later. You get that, where if I have initial conditions and I know what my change in eccentric anomaly is, and with Kepler's equation you can do that, you know, then you will have exactly the radius. So I can compute that. I still need to know what is this change in eccentric anomaly, so I need Kepler's equation. And Kepler's equation, the way we defined it was, you know, M was big E minus little e sine the eccentric anomaly. That means we're defining things back to this, or, you know, where's periapsis and all that stuff. In terms of differences of angle, a bunch of more algebra later, you can rearrange this stuff and write it explicitly in terms of differences of these angles. And then that's what you get out of this stuff in the end. This one is pretty simple. This one takes a little bit more algebra to write out that way. But this is essentially nothing but Kepler's equation again. I have a change in mean anomaly that tells me that this I can compute quickly because I know mean anomaly varies linearly, as you're talking about, right? And then I have to solve this now using some numerical iteration technique, Newton's Raphton's method, something like that. So it's a modified version of how to solve your orbits. And then this just relates all this other stuff, but you can get there. But anyway, it's a neat answer. So fundamentally, it assumes that, hey, I know everything's planar, so therefore this could be a base function. That's what I was thinking for a project. This might be fun for somebody who wants to do. I think for circular chief motions, the relative motion will also be planar. There must be a way to be able to rewrite this in this form. I have no idea what these F and Gs would look like, but that would be more of an open project. So this kind of, I'm not going to start up perturbations. I've got 2 minutes. So let's just start talking about projects then, quickly. What have people done? So with the descriptions, what I encourage you to do is go on scholars.google, something on the web, start searching for formation flying, formation descriptions, relative motion descriptions. There's all these different papers out there. Some of them deal with quaternions and just defining things in a way that the kind of attitude inspired. Other ones are using, different elements. We're using Cartesian, classical elements here, mostly, those two sets. If you wanted to work in equinoctial or Delaunay, if you do the Hamiltonian systems, there's all these different things you could go look at. How do you come up with relative motion description? Some people come up with their own projects where they're taking stuff we're doing in class, and now they want to apply it to, hey, I'm doing a hyperbolic arrival orbit on Mars, and I've got my primary craft and a sensor, and got some relative motion, and and you could come up with a predicting of what the dynamics is, maybe analytically, maybe computationally. You could think about things about the moon and motions there with the formation. So this is all about describing a formation or predicting the dynamics of a formation. Other students have done stuff around asteroids and how formations evolve there. A lot of it computational. The fields get very complicated. We won't be able to use some of these things. This is a series of different ideas I want to throw at you there. Look for some paper like that. And again, my constraint is don't use one of my own papers because it's probably in the book and it's all, I want you to broaden beyond what I'm teaching you and try to pick something else there. The scope has to be reasonable. You'll see, I think on Thursday I'll post the assignments, and you'll have roughly till probably like a month and a half-ish to do this out of the semester. So with the regular classes and everything else you do, often when you pitch me this proposal document, you should say, look, this is the field, this is what's happening, a quick introduction, what you want to study, what's been done. If this is new stuff you want to get engaged in, maybe it ties into your research, and I'd like to apply this here and look at the new coordinate frame transformation, great. But we really want to make sure the scope is reasonable because it's new. Who knows where it goes, right? If it's something that's based on a paper or two, then you go, hey, I've seen this here and I've seen that there, and I want to basically duplicate these results, see if I can validate that stuff that's happening here, make my own simulations, maybe apply it now to a different gravity field model or something, And so then you and I will both argue on the scope. If anything, I tend to downscope it. Students tend to come in, oh, I'm going to do this and that, and this can link to 16 papers. And I'm like, yeah, no, it's not. It's just not possible. So we have to come up with a scope that kind of makes sense. But, if you really feel like, hey, I have great research, and I've already got this code running, and I've got this gravity field model, and I can apply this and this, great, this may work for you, but for the next student who doesn't have that in their research, it may not work, right? And I cannot grade in a way where I'm going, well, they did way more complicated things than another person. It's going to be very individual. So that's why we do a little proposal. You write me a document. I will read everybody's project description and scope in particular. In the scope, it helps if you don't just have a paragraph, but break it down. Bullet 1, set up simulation, doing all this stuff. Expect to take maybe 3 weeks. Step 2, validate, go through this paper. It's going to take another 2 weeks, starting somewhere in between, right? And then break it up into, task 1, 2, and 3, and 4, and I'm going to go check mark. You do those tasks as we agreed, and you do it well, you get an A, right? Nobody can come back and go, well, but they did more than them, and it doesn't matter. It's all different stuff. It's about individual learning. Any questions on that right now? Just start thinking about this and start looking, because you may come back with good questions on Thursday. Hey, I've seen this, or how about that? And you'll have like a week or 10 days to make this little proposal, and it's often quite iterative. So as you see stuff, come chat, and maybe chatting at the beginning of class, you're going to help colleagues and go, ooh, I didn't think about that. That might be a good, interesting way to go as well, Yes, sir.
So the question would be if the projects have to build upon each other, or they're just completely separate?
No, they will not have to be. For some it is. Then they have this fun dynamical system that they can do, and then part B, they try to control, you're doing a hyperbolic reentry and you want to have a particular relative motion while you're doing an atmospheric flyby on Mars or something. You could, but it doesn't have to be. So you're not putting yourself in a particular corner by picking your first project. You may build on that, or you may say, now I like this, I want to do something else. Completely open. Okay, so good opportunities to get something out of this that's very individual, hopefully of interest to you. So I just want to start early, seeding ideas, and the next few lectures every morning, every time we begin, we'll be chatting about, hey, what good ideas do we have floating around? And I think everybody should have something really cool to look at as we go through the rest of the math. Okay, thanks everybody, and I'll see you on Thursday.